Welcome to Lyons Township High School AP Physics. Today we have a problem involving linear and angular motion for a multi-mass system. We're going to throw a little friction in there. So I would suggest it's a block being dragged up a ramp by another block over a pulley that has mass. And there is friction between this block and the ramp. So I would first suggest that you maybe pause the video and give this a quick copy. And when you're ready, come back to me. All right, hopefully you're ready. All right, so we have these two blocks. M3 is dragging M1 up the incline. We have a kinetic friction between block 1 and the ramp. We have some data here. We're going to use that later. And the two things we're going to find real simple. What will the acceleration of your system be? And what are the tensions in the string? Okay. Now, a quick note. Even though there's only one string here, there's going to be two tensions. Because M3 is accelerating down, okay, and I'm making that assumption right now. If we found acceleration to be negative, we're making a wrong guess. But if M3 is accelerating down, then this pulley has to have an angular acceleration clockwise. In order for this pulley to have an angular acceleration clockwise, the tension in this string pulling this way on the pulley has to be more than the tension pulling this way on the pulley. Okay? So I'll call this T1 and I'll call this T2. And we're going to determine those. And if I know that if M3 is accelerating down, that T2 has got to be bigger than T1. Okay? Now when we find the acceleration of the system, we're going to first find it just in variable form, no numbers. Okay, and then we'll plug our numbers in. For the tensions, we'll go ahead and plug numbers in. That's a little easier to do. Now, the next step in a problem like this is to assign it a positive direction. In other words, make a guess as to which way this thing is going to go. Now, I've made M3 pretty big compared to M1 and M2, so M3 is probably going to accelerate downward. So for our system, this is going to be the positive direction, okay? So for M1, up the ramp is positive. For the pulley, clockwise is positive. And for M3, down is positive. So I'm going to draw, there's three objects moving, M1, M2, and M3. So I'm going to draw three FBDs, okay? And this is probably the most important part. If you can accurately draw the FBDs in appropriate form, the rest of the problem is just algebra, okay? So starting with M1, I'll draw that down here. Okay, so there's M1. So you have the tension pulling this way. That's T1, okay? Now, again, a quick note. On this picture, up the ramp is positive. So I'm going to make a little note of that. That's the positive direction, up the ramp, for that one block only. Now, what I want to do is I want to split all my forces into two components, either parallel to the ramp, to that motion, or perpendicular to the ramp, to that motion, okay? So tension is already parallel to motion. I ain't got to do anything to it. We're also going to have friction trying to slow the block down, or at least trying to slow the block down. So I'll label that as force of friction, okay? You're also going to have the ramp pushing upward or away from the ramp, perpendicular to the ramp. That's the normal force. So I'll draw that in, F normal. Now you also have gravity. Now gravity points straight down toward the center of the Earth. We're going to split that up into components. Now we've done that in prior chapters, so I'm just going to write them down here. If you need help with that for physics, AP Physics 1 for Lyons Township, that's our chapter 4 in our book. We talk about that extensively. But if you do that, what you end up with is you have Fg times cosine of theta. If that's your angle, this is the component of gravity that points into the incline. And in here, you're going to have Fg sine of theta. That's pulling down the incline. Now, this isn't quite drawn to scale. T1 should be bigger than this and this add together. Yeah, it's pretty close though, okay? So that's your FBD for M1. That's probably our hardest FBD too. Then we'll go to the pulley. That's M2. Well, and I'll label this, by the way. I'll just label this M1 just so I don't forget. For the pulley, I got to actually draw the pulley out because it's rotating and I have to draw the forces acting at their appropriate lever arms. So what forces act on the pulley? Well, you got T2 pulling this way on it from over here. You've got T1 pulling counterclockwise on it from over there. Now, thankfully, those are already both perpendicular to the wheel. If you draw a radius here and a radius here, both those tensions are perpendicular to the wheel, so you don't have to worry about any angles with those two. Now, you also have two other forces acting on that pulley, at least. You have gravity, so that would be M2G. And then also, it's being held up by this, otherwise it would come crashing this way. So there's a force like up in that way. Technically, it'd be a normal force. I'll call it like Fn2, okay? You could also call that a tension force depending on how you've got this pulley mounted, but it's pretty much a normal force. Now, a quick note. Since this pulley is not moving up, down, left, or right or anything, the net force on the pulley's got to be what? That's got to be 0. So, by the way, you could find Fn2. Now, I'm not going to ask you to do it in this problem, but if once you have T1 and T2 and you know M2G, force of gravity, you could find Fn2, both the magnitude and the angle it points at. So just because you know the net force on the pulley is 0. However, the net torque on the pulley is not 0. So first of all, do all 4 of these forces cause torques? Well, the 2 purple ones I've drawn, they act through the axis of rotation. They have 0 perpendicular lever arm. They have 0 radius to our axis. So Fn2 and M2G, they don't cause any torque. So when I'm doing my net torque equation, I can ignore the 2 purple forces. Okay. And then finally we have M3. Oh, man, I almost forgot. Positive for this guy is clockwise, okay, from our original picture. Now I'll go ahead and draw M3. I'll do that right here. Now he's easy. He's got gravity pointing down. That's FG3. And by the way, I'll make a quick note. I'll call these FG1. Okay. I don't ever like to have the same letter in 2 FBDs unless it's actually the same thing. Okay. So FG3 and FG1, they're going to be different values, so I'm going to label them different. So I got FG3, and then the string is trying to hold it back. We'll call that's T2. Okay. And for this dude, down is positive. That's our positive direction. Okay. And again, personally, I think this is probably the hardest part of the whole problem. Okay. Now, I will do one last thing down here on FBD number 1 over here, the force of friction. How do we calculate that? So, and this will be for my equation later. Force of friction is mu sub k times Fn, right? And in this problem, Fn is going to equal this. So we got mu sub k times Fg1 would be m1g cosine theta. Okay. All right. So that's going to be friction. That's going to end up going in an equation later. Okay. All right. So then I'm going to write Newton's second law for each individual object. Okay. So I think I'll do it on the next board. Oh, old problem. Okay, so we've got net force on block 1 equals M1A, okay? Oh, one more note. Block 1 and block 3 are going to have the same linear acceleration because they're attached. So there's just one A in the problem, acceleration, okay? All right, so net force on block 1 equals M1A1. Well, in this problem, up the ramp is positive, so that is positive, and these two are negative, okay? So I write T1 minus force of friction minus Fg1 sine of theta equals M1A. Now notice subscripts are critical here, okay? And then we know T1 minus FF, which was mu sub k times m1g cosine of theta. There's your friction. And then minus FG would be m1g sine of theta equals m1a. So there's one equation. That's for block 1. Okay. For the pulley, it's spinning, so we got to do net torque equals I alpha. So for block 2, I do net torque equals I alpha. Okay. And this is on 2. Okay. All right. Now again, for this guy, the two purple forces don't cause any torque. T2 causes a positive torque. T1 causes a negative torque. So for torque, it's R cross F, so it's R times T2, that's our positive torque, minus R times T1, that's our negative torque. We're going to assume that the pulley is a solid disk. The moment of inertia, I, for a solid disk is 1/2, it's m2 r squared. And then alpha. Okay, well, we need to get alpha in terms of A. Well, alpha is equal to A over R. Okay. Now, having said all that, we can start canceling a lot of stuff out, which is kind of nice. This R will cancel with one of those. This R cancels with these two. And you get a pretty simple equation. T2 minus T1 equals 1/2 m2A. So there's a second equation. Now, our problem is we got 3 unknowns. We don't know T1. We don't know A, don't know T2. So we have to come up with a third equation, okay? Well, that's where you go to the third block. Now again, for him, down is positive. We'll do net force equals MA for him. So if I do net force on block 3 equals M3A, well, he's pretty easy. It's FG down, which would be M3G down, and you got T2 up, and that's equal to M3A. So that's your third equation. And we didn't introduce any other unknowns. We have A and T2 and T1. That's our 3 unknowns. We got 3 equations we could solve. Now, there's lots of ways that you can solve these 3 equations. I'm trying to get A by itself. I'm going to simply add them together, okay? Now, I'll write them one after the other. So I'm going to write this one first. Well, I'll write this one underneath that one. So we've got T1 minus mu sub k m1g cosine theta minus m1g sine theta equals m1a. And I'll write this one directly underneath that one. T2 minus T1 equals 1/2 m2a. Now, again, I'll make a note, a very important note. Subscripts are important. If you just put m in here, you don't know what's what. Okay, so you got to keep track of M1, M2, M3, and so on. Now here's the cool part. If you add the equations together, I have a negative T2 and a positive T2. I have a positive T1 and a negative T1. All right, and so what do you end up with? You end up with that's our positive term, M3G, minus that, so minus mu sub k m1g cosine theta minus this, which is m1g sine of theta, equals, on the right side of each equal sign, what do I got? Well, I got an M3A, I got an M1A, and I got a 1/2 M2A. And I'll write those in order. So we got a M1A plus a 1/2 M2A plus an M3A. And we've almost got A. To get A by itself, you would factor the A out here. So you'd have A times M1 plus a 1/2 M2 plus M3. And you divide everything by that, and that's your term, or that's your expression for acceleration. So my final acceleration is all this, M3G minus mu sub k M1G cosine theta minus M1G sine of theta all over M1 plus a 1/2 of M2 plus M3. Okay, that is the expression for acceleration in terms of the givens. That's the algebraic expression for it. Now, we do have values for all of that, So we can go ahead and get a number out of this. So let's see here. M3 is 6. We know G is 9.8. Mu is 0.2. M1 is 2. Theta is given as 30 degrees. M1 is 2. This is 30 degrees again. This is M1 is 2. M2 is 4. And M3 is 6. Okay. If you plug all that stuff in, I got an answer of 4.56 meters per second. Meters per second. So you can double check me there, but if I have those values right, then the acceleration should be 4.56 meters per second. So about half of gravity. Okay. So that's the acceleration that you get. Here's the algebraic expression, and here's the numerical value for it. Now, to go back and find your tensions, I do want to make a quick note. Okay. If I go back to M2, for instance, its weight, if I do M2G, it's 4 times 9.8, which is 39.2. So this number here is 39.2 newtons. Okay. Oh, I'm sorry, that's M3. Apologize. It's 6 times 9.8. Whoops. 6 times 9.8, oh gosh. Let's see, 6 times 60 minus 58.8. So this is 58.8 newtons. Okay. Now, how should T2 compare to 58.8? All right. Well, which way is this guy accelerating? He's accelerating down. That means our downward force has got to be bigger than our upward force. So T2 better be less than 58.8 when I get an actual value for that. Well, here's the cool part. If you go back to, let's say, this equation here, okay, move your T2 over here, move your M3A over there, make it negative. You got T2 equals M3G, which is your 58.8, minus M3A, which is 6 times your 4.56, okay? If you do all that, I got a value for T2, and I'll put it in the FBD. I got a value of T2 to be 31.4 newtons, which is definitely less than 58.8, okay? And you can do a similar thing over here. You know that T1 has to be bigger than this plus that, okay? Now, to find T1, you've got a couple options. You could either use this equation here, because you have all these values now except for T1, or you can use this equation here. I kind of like this one. You put T1 over there, make it positive, take your 1/2 MA, put it over there, make it negative. So T1 is equal to T2, which we've got, 31.4, minus 1/2 M2A. Okay, hold on. Oh yeah, so T1 equals T2 minus 1/2 M2A. That's 31.4 minus 1/2. M2 is 4, and A is 4.56. So you should get 31.4, twice that. I'll just do it in a calculator. All right, so you get 31.4 minus 2 times 4.56. I got a 22.3, okay? So I'll put that in the FBD. So this is 22.3, approximately newtons. Now, by the way, going back to this picture, I'll put those in there too. This is 22.3, and this is 31.4. Again, a reminder, we talked about this. If this pulley is going to accelerate clockwise, T2 has got to be bigger than T1, right? So, and there you see it right there, okay? All right, so a lot of work. That's a pretty complicated system, right? You got 3 objects moving, one's rotating. Yeah, that's pretty tough, okay? I do hope that that was helpful, and thank you very much.